sometimes it is not possible to differentiate an equation directly because it is not a function. But by using a technique called implicit differentiation, we can find a derivative. Hi, my name is Tom Atwater, and in today's lesson, we will step into the mathematical realm of implicit differentiation. Implicit differentiation. To use implicit differentiation to find dy dx, we treat y as a differentiable function of x and differentiate both sides of the equation with respect to x, using differentiation rules for sums, products, quotients, and the chain rule. Then we solve for dy dx in terms of x and y together. Let's look at an example of implicit differentiation. We're going to find dy dx for x squared times y plus xy squared equals 6. So in this case, we're going to take the derivative of x squared y, which means we have to apply the product rule. So we take the first function, x squared, and multiply it times the derivative, which is dy dx of that second function. Plus, we take the second function and multiply it times the derivative of the first function, which would be 2x, and then dx dx, which of course is just 1. Then we have to apply the product rule to this second term. So we take the first function, x, and multiply it times the derivative of the second function. So that's 2y dy dx. And then we add to that the second function times the derivative of the first function, which is x, and the derivative is dx dx, which is 1. And then finally, that's equal to 0 because the derivative of a constant is 0. So now what we want to do is look and rearrange this equation so that we can get the dy dx's together and anything that does not include dy dx to the other side. So what we have is dy dx times x squared, and then here we have it, so it's plus 2xy, and that's in parentheses. The other terms don't have dy dx in them, so we're going to bring them over to the other side. And those terms are 2xy, so that would be negative, and y squared, which would also be negative. So now what we can do is we can solve for dy dx, which is going to equal negative 2xy minus y squared all over x squared plus 2xy. And that gives us the derivative dy dx. Now, it's, of course, in terms of both x and y, but at least we were able to find the derivative through this method of implicit differentiation. Let's try another example. Let's look at find dy dx for the equation x plus tangent of xy is equal to 0. Find dy dx means that we're going to use implicit differentiation on this. So we take the derivative of x, which of course is 1. Then we take the derivative of tan, which is secant squared, and it's of xy. But now we have to use the chain rule because of the xy that's like the inside function. But in using the chain rule, we have to differentiate x times y, which means we have to use the product rule. So that tells us that we take the first times the derivative of the second, dy dx, then plus the second times the derivative of the first, dx dx is just 1. And of course, the derivative of 0 is 0. So now we need to distribute the secant squared because we need to eventually isolate dy dx. In order to do that, we need to be able to separate it out. So what we have is, I'm going to move the 1 to the other side at the same time. So we're going to get secant squared x y times x dy dx plus y times secant squared of xy, and that equals -1. Then I can take and move this to the other side, which will then allow me to divide both sides by this coefficient of dy dx. So what we'll have is dy dx will equal -1 minus y times secant squared of x y all over this coefficient, which I'm going to rewrite as x secant squared of x y. And so that's my function for dy dx in terms of x and y. So you can see that implicit differentiation is a great technique for equations which are not clearly solvable of y in terms of x. Let's try one in which we need to find the second derivative. Find dy dx, then find d squared y dx squared for the equation y squared is equal to x squared plus 2x. Again, implicit differentiation. What we have is the derivative 2y times dy dx. And let me clean that 2 up a little bit. So that's 2, much better, equals the derivative of 2x. I'm sorry, of x squared is 2x, and of course times dx dx, which is 1, plus the derivative of 2x, which is just equal to 2. So dy dx will equal 2x plus 2 all over 2y. And that gives me dy dx, but we want to find d squared y dx squared. So we will have to differentiate once more. Let me go to a clean screen. And we had, to start, dy dx equaled 2x plus 2 over 2y, which I'm going to simplify to x plus y over 1, because obviously that will be a little bit easier to differentiate this second time. So on the left-hand side, when we take the derivative of dy dx, we get d squared y dx squared. On the other side, we have the quotient rule. So it's equal to the denominator times the derivative of the numerator, which is just 1, minus the numerator times the derivative of the denominator, so dy dx, all over the denominator squared. let's simplify that a little bit so that we have d squared y dx squared, and that's going to equal y minus x dy dx minus 1 times dy dx all over y squared. What we want to do is make a substitution here where we can go back to the fact that dy dx is equal to x plus 1 over y. And we'll make that substitution inside here, and then we'll be able to simplify it even further. So we need to remember that we have y minus x times dy dx minus dy dx over y squared. And let me go to a new screen. So we had d squared y dx squared was equal to y minus x times dy dx, which we now are going to make the substitution x plus 1 over y, then minus 1 times dy dx, so minus x plus 1 over y, and all of that is over y squared. When we simplify that, we're going to get that it's equal to y squared minus the quantity x plus 1 squared. And that's all going to be over y cubed. Now we can make one more substitution here. From the original equation, we know that y squared is equal to x squared plus 2x. Y squared equals x squared plus 2x. And if we make that substitution in these places, we will get d squared y dx squared is equal to negative 1 over y cubed. And that gives us the second derivative of that original equation. In the law that describes how light changes direction as it enters a lens, the important angles are those that the light makes with the line that's perpendicular to the lens surface. This is called the normal line to the surface of the point of entry. If we take a look at this figure, you can see that we've drawn our tangent line. We're looking at this point as the point of entry. We have our tangent line, which of course is tangent to that point, but then our normal line is perpendicular. You can see it right here. It's perpendicular to the tangent. And then what happens is, depending on the curvature of the lens, you get a different light ray coming in and coming through the surface at some particular angle that's based on the surface curvature. Well, we can use implicit differentiation to find tangents and normals to any surface. Let's look at an example where we're going to find the lines that are tangent and normal to the following curve. X squared times y squared is equal to 9 at the point -1, 3. Again, we're going to have to use implicit differentiation, and we're going to have to use the product rule. So we start off with the first function multiplied times the derivative of the second function. So 2y times dy dx plus the second function, y squared, times the derivative of the first function. So it's 2x, and then, of course, dx is 1. And that's going to equal 0 because the derivative of a constant is 0. Now we can solve this, and we can say that dy dx is equal to negative y, or actually let's put the 2 out in front, negative 2y x, and it's y squared, sorry, and then divided by the 2 out in front, and we have y x squared, which of course that whole thing simplifies. The 2's cancel, the x on top cancels out one of the x's on the bottom, the y on the bottom cancels out one of the y's on top, and we get negative y over x. Well, what we need to do now is, this is, of course, the slope, right? dy dx, the first derivative is our slope, and we're trying to find both the tangent and the normal. So in order to find the actual numerical value of slope, we have to plug in the points negative 1, 3. So when we do that, 3 on the top, the negative 1 on the bottom, so we have negative 3 over negative 1, which is a positive 3. Let me go to a clean screen where we can begin to write the equation first for the tangent. We know we have the point, which we just used, of negative 1, 3. So that's y minus 3 equals the slope we just determined was 3. And now we're going to multiply that times x minus a negative 1. Simplifying that a little bit, we end up with the equation for the tangent y equals 3x plus 6. To find the equation for the normal, we must remember that the normal is perpendicular to the tangent. And if it's perpendicular to the tangent, it means it has the negative reciprocal slope. So for the normal, it would be y minus 3 equals negative 1/3. Negative 1/3 x minus the negative 1. And we can simplify that a little bit, and once we simplify it as far as possible, we end up with y equals negative 1/3 x plus 8/3. And so this is the tangent, and this is the normal. And we used implicit differentiation to help us find both of those. Well, we're going to change gears a little bit here and look at something called the power rule for rational powers of x. And that tells us that if n is any rational number, then the derivative of x to the n is equal to n times x to the n minus 1. Now, yes, we've seen this in the power rule, but the difference here, as you can note on the bottom of the slide, is that we're dealing with, if n is less than 1, then the derivative does not exist at x equals 0. And we're talking about rational powers now instead of just integer powers. Well, let's take a look at an example where we will use that new rule. Y equals the square root of x, and y equals x to the 2/3. Well, remember that y equals the square root of x is really x raised to the 1/2. So now we can apply that new rule, which tells us that it's 1/2 x raised to the negative 1/2. And you could take that one step further and say that this is equal to 1 over 2 square roots of x. What about the next one, y equals x to the 2/3? When we want to take the derivative of that, y prime, we get 2/3 x raised to the negative 1/3. And we could simplify that just a little bit and say that it's equal to 2 over 3 times the cube root of x. Well, now it's time for you to try a problem which involves using that rule for rational powers. I would like you to find dy dx for y equals 2x plus 5 quantity raised to the negative 1/2 power. Pause the video while you work on this problem, and when you're finished, restart the video to check your solution. Welcome back. Let's take a look at the derivative for this particular problem. So y prime will be equal to negative 1/2 times 2x plus 5 raised to the negative 3/2. And we have to use the chain rule here because of the inside function, so it's times 2. Let's simplify that a little bit, and we get y prime equals the 2 cancels, and we have negative 2x plus 5 raised to the negative 3/2 power. And that's the answer to the problem that you just worked on. Great. Well, in today's lesson, we learned about implicit differentiation, a very powerful tool. Be sure to work the exercises that your teacher assigns, and we'll see you next time.